Hello to everyone. The title of this contribution is Extraction of High-Level Features and Labels in Multi-Label Classification Problems. Multi-label classification is a type of classification where each of the data's objects has associated a vector of outputs instead of being associated with a single value. This particular classification case requires additional efforts to extract relevant features describing both inputs and decision domains, since the boundaries regions of decisions usually overlap. Deep learning is a promising avenue of research into the automated extraction of complex data representation at high abstraction levels. These algorithms develop a hierarchical and layered architecture of learning and data representation, in which higher-level features are defined in terms of lower-level features. Pooling layers provide an approach to downsample feature maps by summarizing the presence of features in patches of the feature map. Several authors have proposed MLC solutions inspired by deep learning techniques, in which data have a topological organization. This is recognizing faces, coloring black and white images, or classifying objects in photographs. However, while it is interesting to recognize faces or classify objects in images and videos, the truth is that there are other domains in which the data do not have a topological organization. For example, when using numerical descriptor to encode the protein, two distant positions in the sequence might be close to each other in a three-dimensional space. That behavior could not be captured with local pooling methods. In those cases, using a standard pooling operator might have little sense, even when the problem at hand could benefit significantly from a deep learning solution. From them, we propose a deep neural architecture to extract high-level features and labels in MLC problems. Unlike the classic use of pooling, this approach does not require pooled pixels but problem feature or labels. This architecture is composed of several stacked association-based pooling layers, built starting from the feature and the labels at the same time. The first pooling layer comprises neurons denoting the problem feature and labels, whereas in deeper pooling layers, the neurons represent high-level features and labels extracted during the construction process. Each pooling layer uses a function that detects pairs of highly associated neurons. This is, they fulfill a certain association threshold, while performing an aggregation operation to derive the pooled neurons. The first variant uses Pearson's correlation to estimate the association degree between two neurons. As a second variant, the entropy is computed in the information granules generated from two features or labels. The rationale behind this variant suggests that two features or labels can be associated if the granulation generated from them have equal entropy. In this way, it is not required that either the feature or label have a certain degree of correlation. The idea of this second variant is to obtain a granulation of the universe where each feature or labels define an indiscernibility relation. The information granules add the set of indiscernible objects concerning the feature or label under consideration. In this way, it is verified if the covering or partition generated by two features or labels induce similar entropy values. Then, the pooling process is repeated over aggregated features and labels until a maximum number of pooling layers is reached. Once the higher level feature and label are extracted from the datasets, they are connected with several hidden processing layers. Finally, a decoding process is performed connecting the high-level labels of the original one to one or more hidden processing layers. The numerical simulation of several MLC datasets show a significant reduction in the number of problem features and labels. This is, reducing up to 96% and 87% respectively. Pearson's correlation does not seem suitable for datasets having a low correlation among their features or labels. However, the second variant reports higher reduction values in datasets having low correlation values among their features and labels. Our proposal that does not aim to increase the prediction rates but reduce the number of deep feed-forward networks parameters without harming the discriminatory power. Thank you very much.